Good morning. Welcome to this lecture. I just go straight into the lecture. Do let me know if you can hear me well. And if you can't, so if I'm breaking, the quality is not good, just let me know and I'll change to another network. I noticed the other day or yesterday that the network here sometimes is not able to support. So if that's the case, just let me know and I'll change. Okay, great. So some of you have said you can hear me perfectly well. That's good. If that changes, do let me know. So I've shared my screen. We were talking about registers at the end of the last lecture. Before that, we had finished counters. Now, the registers, as we said, are based, or they are the registers generally store data. So memory, like your hard disk, so to speak, is made up of a combination of registers. So many of them. Now, a register is made up of a flip-flop, but it can also be made of capacitors, which use charges. We'll look at that in the near future. But the ones we are looking at are based on flip-flops. We said that each flip-flop, or at least we know that each flip-flop stores one bit, and that bit is this, we call it the state of the flip-flop, and it is the value that appears at its output, not its input, but its output. Now, when it comes to registers, we see that we name registers based on how we input data and how we output data. If we input data in a serial way, meaning one bit at a time, then we usually say that that is serial in, okay? And if we output data in, if we input data in parallel, meaning that all the data goes into all the flip-flops simultaneously, then we say parallel in. And this also happens at the output. So for instance, if we input data in a serial way and output it in a serial manner, then we have serial in, serial out, or SISO. Parallel in, parallel out means that we input data in a parallel way and output it also in a parallel way. So by parallel, I mean that all of the flip-flops, you can feed data into all of them at the same time. Maybe you have 4 flip-flops, which would be a 4-bit register, and you have a 4-bit word, or so-called a nibble, and you can feed it into the flip-flops all together simultaneously, meaning the whole word goes into the flip-flop. If it's synchronous, then after one clock symbol or clock input. We actually looked at the people parallel in, parallel out, the 74 ALS174. If it's ALS, it is TTL technology. If it is HC, it is CMOS. So you can see, for instance, here that we have D flip-flops. These are 6, so we have a 6-bit. This is a 6-bit register that is parallel in, parallel out. You can see here that we are able to clear. The master reset is active low. So if we have a 1 here, we cannot clear. That means that the natural resting place of that state going into the clear should be 1, because if it is 0, then it will always clear, and we know that clear is the overriding input. And so you have, if you have a 0 here, it becomes a 1 here, and it becomes a 0, and that will clear. If you want to not clear, then you should always keep that high. But you can see that in general here we have, let's say we have D5 as a 1, as a 0, 1, 1, maybe 0, 1. You can see that all of the flip-flops are clocked at the same time. This same clock signal is clocking all of them, and now this is an this is a synchronous register. Most registers are essentially synchronous, especially when we are inputting data or outputting it. You can see that at the output, if we give the right clock transition, in this case the negative going transition, then the information that is available at the input will shift to the output. So meaning that after the first clock transition, we have our 1 here, we have our 0 here, our 1, our 1, our 0, and our 1. And obviously that information being at the output can be picked out on the outside. So when you have a register like this, it will have all the input lines, 6 input lines, and 6 output lines, so that you can feed information here and push it out here all together simultaneously. Okay, we talked about this actually, so we'll just continue. You remember how I was explaining this from the last lecture. Now let us look at a serial in, serial out flip-flop, which is a 166, both CMOS and TTL. You can see here that actually we have our serial data going in there. Okay, this is the serial input. Now this flip-flop, this register is special in a way that it also has capability to perform parallel loading, like a parallel input. So these are here for parallel loading. It means that yes, we input our data serially, but if we had a full word and we wanted to feed it into the register at the same time, we can load the flip-flop as well. So there's that special capability that it can do both parallel input and also serial input, but we essentially look at it in this context as a serial in, serial out. It has an active low clear input, and it has, usually when it is serial in, you usually have your flip-flops like this. And so we move information from one flip-flop to the other, meaning that you input it here and you keep picking it out from here. This is usually similar to a shift register, or shifting data through the flip-flop. And so here we have a shift and a load, parallel loading command. If this is fed with a 1, it means we are going to shift. If it's fed with a 0, we are going to load. So if you are shifting, you should have a high here. And if you want to parallel load, meaning that you have provided some inputs there and you want to feed them into the register or simultaneously, then you put a 0 and you load the flip-flop. Now we have these two that we have not seen before. One is the clock that we know. The other one is the clock inhibit that we have not seen before. The clock inhibition allows us to prevent the clock signal from reaching the flip-flop. So we can, for instance, in here, we can say in here that we have an OR command, meaning that we have an OR command. On one side, we have the clock, which is like this. And on the other side, we have clock inhibit. Now, if this clock inhibition is 1, then at the output, we will always get a 1, because this is an OR gate. It doesn't matter what the clock is. As long as the clock inhibition is 1, the output will be a 1. And so you'll never really get those active transitions of the clock. So if we want to shift, if we want to inhibit the register, we just make clock inhibition 1. Otherwise, we make it a 0. And if it is a 0, then when the clock is 0, this will be 0. When it is a 1, that will be a 1. So you can see how the clock inhibit works. It is all together with the clock itself, so that you can choose, for instance, to lock it out, to disable it. Yeah, something else that I can talk about here, pretty much that. Maybe this is that because it is serial in, serial out, you do not access the other flip-flops. So it's not similar to this where you have the 6 outputs. You have only one output, which is the output of the last flip-flop where the data is coming out from. Right, so let us look at this table and try to understand it. Here we have inputs, our inputs are these, and we have outputs, and then we have QH. This is the actual output that we see, but we know what is happening inside since it is a shift, a sort of shift or shift register type. Now these internal, they just put 2, but it's really from QA, QB, QC, QD, QE, QF, and I think QG, 7 of them. So this is an 8-bit serial in, serial out register. Now, if we want to clear, we make this low. And once that is low, it doesn't matter what all others are. We are just going to clear, and by clearing, we are making all the flip-flops low, all of these, and obviously the output will also be low. In other words, the clear input clears all the flip-flops. I'm going to be showing you a more detailed circuit of this. Now, if we don't want to clear, then we must make sure that all these are high. So otherwise, outside of that one command where we clear, the clear should always be high so that it is not active, it is inactive. Then we see the clock inhibition. We have a low on the clock. We said that if we have a 0, we have a low, and also the clock is low. Now, if both of these are 0, then there is no clock transition. And if there is no clock transition, then this command, you can see here, this is we don't care. What this means is that both the shifting and the loading are synchronous functions. As long as there is no clock, you can neither shift nor load. So, that's it. And what happens to the flip-flops? The flip-flops retain the previous, there is no change because you have neither shifted nor loaded and nor cleared, in fact. So there is no change there. Otherwise, if we say this is low, meaning that we are now going to load, and the clock inhibit is low, meaning that our clock can go through to the output, and we get the positive going transition, we are going to load, so it doesn't matter what is at our serial input. Okay, it doesn't matter because we are going to load. And if these are the values that we are loading, you can say that they are going to appear on the flip-flops, all the way from A, B, C, D to G, and obviously at the output, we will have loaded H. Okay, those are binary numbers, of course. In the next one, we have high, meaning that now we should be shifting. We can't load when we have high, we shift. The clock is still low, we get an active going transition, and now that these are the conditions for shifting, basically. It means we can get our clock, and so if our serial input is high, then the high is going to go into the first flip-flop, here. Our serial will go there. What was here will go there, and I think you can see that now Q, this one, by N it is like what was here has shifted here, what was here has shifted here. That is the shifting all the way to G, shifting to H, and what comes out of H is the output, which was at G. You can see Q, GN. That was the value that was at G has now shifted to H, and what was in H obviously has been pushed out and maybe lost or taken into some other circuit. If we look at this, if the input at the serial input was a low, the low is the one that goes into A, but the rest is the same because we are shifting them forward. Finally, if the clock inhibition is high, as we saw here, if this is a 1, then the output will always be a 1, irrespective of that clock. So that means that we don't care what is at the input of the serial input, we don't care what is at the parallel input, and we really don't care whether we are shifting or loading, because the clock the clock is not there, and so you cannot perform a synchronous activity or function without the clock. Okay, so that is how that works. This is actually its circuit, so you can see that you have 8 inputs, but you have your serial input here. Okay, serial input here. This is the clock inhibit circuit, which we have already looked at. It is an OR gate and the clear. Okay, this is the clear circuit. It's not complicated, but let's look at an example. So let's say that we have a 1 here. Let me use this. I got this one, so that we can see a bigger diagram. So if we want clear, we put a 0 here, and if we put a 0 here, then here it becomes 1, and you can see that that's an active high input. The reset is active high, so the 1 will reset the flip-flops, all of them, including the ones here. Now, if we want to inhibit, we make that a 1. If we make this a 1, it doesn't matter what the clock is, it will always give a 1, and the 1 going into there will mean that there is no PGT ever. It's just constant 1. So that's how we can inhibit. If we don't want to inhibit, we make this 0, meaning that, if we had a clock, it can go through that. So that is how we are basically using that OR gate as we are using the clock inhibit as an enabler or disabler. Those disable or enable inputs that we did in first year. Okay, so now let's say that we want to shift serial, so we have our serial input here. We have our shift load inputs there, and we have our parallel inputs there. Now let us imagine that we want to shift. If we want to shift, we make this a 1, right? If we make this a 1, it means we have a 0 here and a 1 here, because you can see that we have a 1, we invert it to a 0, and we invert it to a 1 here. Now let's see what happens. If we have a 1 going in here, it means that whatever is at serial will go through there. If it is 0, we have a 0, because that's a high. If it is a 1, then we have a 1 going in here. Let's assume that serial is 1, then we have a 1 here, because it is 1 and 1, which is a 1. Unfortunately for this side, if we are shifting and we have a 0 here, the 0 goes there, and 0 and whatever number will always be 0. So you have a 1 and is 1 or 0, meaning that you have a 1 there. And if you have a 1 there, then when you get your clock, that one, this is a D flip-flop, so the 1 will come here. It means that what was here will have shifted there, and so on and so forth. Okay, great. Now let's assume that we were loading. If we are loading, we have a 0 there. And if we have a 0, we have a 1 here. And then we have a 0 here. This 0 will come into this AND gate, and it means that whatever the serial in is, we will still have a 0 outside that AND gate. However, the 1 here will join here, so you will have, in this circuit now, you have 1 and A, meaning that you have your A here. Okay, this 0 or A, meaning you'll get an A, and so you can parallel load all of them. In other words, you can see that based on this, we can disable shifting and enable loading, or disable loading and enable shifting. So yeah, so this is an excerpt, a piece of this larger diagram. I'm not going to ask you to draw this, you shouldn't be worried, but I can certainly bring something like this and create this table for you to fill in some missing gaps. Okay. Please, if you have any questions, type in the chat. Otherwise, I hope that you're following. So this is a 166 74166 IC. It is a CISO, but it can also perform parallel loading. And okay, the loading works. Parallel loading is essentially, okay, so you have, I actually don't know, I didn't get your question quite well, but parallel loading means that you have your code word, say 1011, and you have it at the inputs here, and you give a command, and they are shifted into the flip-flop simultaneously. That is called parallel loading. We are loading the flip-flop in parallel. Shifting is different, because with shifting, we have our 1011, And so we start with the least significant bit, which is this one. We first shift. Okay, let me draw 2, 3, 4. We first shift the 1. The 1 goes there. And in the next clock, we push this 1 to there, and this 1 comes here. In the next clock, we now move the 0 here, move that 1. Now this 1 goes here, and that 1 goes there. In other words, we are shifting our data through the register. And if we wanted to keep this 1011 into here, that means that when 1 reaches here, we know that the 0 will be here, and the 1 is here, and the 1 is here. And then we can stop counting. We can stop giving the clock pulses so that our data can stay within the flip-flop. Obviously, if we give more commands or clock transitions, the active clock transitions, then this one will be pushed out, and the data, your data will be pushed out of the register. Yes, the output is only serial. As you can tell from here, we are able to parallel load, but we are only able to access our output through the last flip-flop. So that makes it serial. In fact, most of the time, all this is embedded within, embedded within the substrate. You cannot really access it, okay? You can only access the inputs and the outputs. The rest of the inside, you can't see it, but at least we know that this is the construction within that register. What is the effect of passing to the data, pushing? What do you mean, Tom? With the table, what is the effect of parsing to the data? I don't get your question. What do you mean parsing? With Nyeko, the table is quite large, but really what we want to do is we are looking at what combinations here. We are looking at what combinations they either give us clear. So you can see the low will clear the flip-flop, meaning all your flip-flops are low. That is what clearing does. If we don't want to clear, we must keep our inputs high, our clear inputs high, because it is active low. So if it's high, it will be inactive. That means we are able to do the other functions that otherwise the clear would override. I said here that if this is low and that is low, it means there is no clock, basically. If the clock is kept low, then there is no transition. There is no energy, there is no edge. There is no positive to negative or negative to positive. And so we will be having no change through the flip-flops. If we put this low, it means we want to load. Okay, you can see the load has a bar, so it's the load that is active low, shift is active high. However, if we want to load, we have to make the clock inhibit low so that we do not inhibit the clock, and then give the right transition, which is the positive going transition. You can see here, there's no bar, so there's no bubble, so it's positive going transition. And once we are loading, we don't care what the shift, sorry, the serial input has, because we are not going to use that input. So but you need to provide the information that you're going to parallel load into the register. And after giving that command and getting the clock, this data will appear in all the 8 flip-flops. If the shift is high, it means we now want to shift. If this input is high, we want to shift. We can't load unless it was low. And if this is low, we get the clock. Then we need to know what is at the input, the serial input. If we are going to shift, we look at the serial input. It can be high or low. If it is high, the high goes into the first flip-flop. If it is low, the low goes into the first flip-flop, and the rest just shifts one position forward. Okay, as we know how shift registers work. And finally, if we inhibit the clock, meaning we give it a high, if we give it a high, then the clock can't go through to the clock input. It will just be one level, and then we don't really care. We can't shift or load. We don't even care what all these inputs are. there will be no change. Okay, all right. I think, John, which state inhibits the clock? I think if you know, if you remember how gates work, you should be able to do that. You have, actually, I think I've talked about this like 10 times. You have your clock inhibit and then your clock. How do you not remember how an OR gate either enables or disables an input? If you don't remember, guys, you need to go back to chapter 3, chapter 4, and chapter 5 and revise, because to me, we did that and you should know it. Now, this is our maybe positive going transition. If I make this a 1 and a 0 is a 1, sorry, a 1 or a 0 is a 1. A 1 or a 1 is a 1. So if my clock inhibit is at 1, that means I cannot get a clock transition. But if I make this a 0, it really means that whatever the shape of this, it will be the one to go out to the output. Cuts, my question on the clock is, if it's high, yes. So why isn't the clock X on the last row? On the last row, let's see. Well, you could say X, it wouldn't change anything, I think. I think you could say X, because once this is high, then it doesn't matter if we get a transition or not. And so I think you're right that you could make that X. It's a don't care really state. But if you make it this, it still shows that actually there is no change much as it comes through. But I think making it no change perhaps is more technically correct. Right, let me see if there are any more questions. Please pardon, okay, on the last count in the table. Yeah, the last count in the table is that you have a high, so you can't clear. You have a high clock inhibit, so you are inhibiting the clock. And so that means you can neither shift nor load, which is why we have don't care. The serial input, we don't care. The load input, we don't care. But as somebody just mentioned, we could also have made this don't care. But then out here, it is no change. Right, let's move on to this. Now, this is quite interesting. And in the book, it's like this, but I did a table. I did a table because, you know, sometimes if you don't see the table, sometimes it's better to draw the table so that you can see things more clearly. You can see here that you have your inputs are all 0, 0, 0. Those are your parallel inputs. Your serial inputs are here. Okay, so you can see the serial inputs keep changing 1, 0, 1, 0, whatever, whatever, whatever. Now they need you to tell us what QH would look like. And it is very easy to draw it like this when you have a table like that. But without a table like this, it's really difficult to know, because remember, information is shifting. Now, the important information to see here is that we are looking at the clock transitions and they are the positive going transitions. Maybe we should see that the clock inhibit is held low so that we activate, we keep the counting or the loading and the shifting active, okay? If clock inhibit is held to 1, we are neither going to load nor to shift. The other thing is that this is held at 1, meaning we are only shifting, we never load, right? So that's also good. Now, the problem is that you have 8 flip-flops in here. 6, 7, 8. This is the one that gives you that. So information keeps shifting through this, but we only want to know the waveform at this point. It's quite difficult if you do not have a table. Let us look at serial input. At this point, it's a 1, then it is a 1, then it's a 0, then it's a 0, it's a 1, and so on and so forth. Let's look at this table. I said that before the time T1, okay, you can see based on here, we have T1. Before time T1, by the way, we cleared. Before time T1, we cleared. So by the time T1 came in, the clear input had gone back to high, meaning that we can now begin shifting. Before This is clear, it was 0, and the serial was 1. At this point, you can see serial input here is 1. Was 1, and so obviously if we clear, then everything is 0, 0, 0, meaning that our output at QH is 0. By the way, these are the 7 flip-flops. The 8th one is the output, so I've kept them separate. The 8th one is the output. Now at T1, our flip-flop, our input, serial input is 1, and the next one will be 0, and so on. So I've put all this in the table. Now at T1, we are able to shift, meaning that's why all this is high, meaning that we cannot clear. Clear is impossible. So if this is our input at time T1, it means that this input will be moved there. We are now going to start shifting, meaning that it comes here, that comes there, that comes there, that comes there, that comes there, that one there, and this 0 goes there. Now the next input is 0, meaning that the 0 now will be shifted into the register. It comes here, that goes there, and so on and so forth, meaning that that goes there. We are going to continue shifting. This one will come there, that one will come there, and so on and so forth. So now you can see that from T1 to T7, we have been shifting zeros through the through the register coming out at the output. So T1 to T7, QH, our output is always 0. Let's just cross check to make sure it is correct. From T1 to T7, it is 0. Then we get our first one, T8, we get a 1, which is here. Then we get 2 zeros, which are these. Then we get 2 ones, which are those. And 0, 1, 0. So really, the whole point is that you just keep shifting. That is from there, that is from there, that is from there. As we feed in information, we remember that information is shifting through the flip-flops. I would like to encourage you to go and try to do this, to create a table for this on your own so that you can understand it. And by the way, you could create smaller examples. So instead of having like 8 bits, you could do 4 bits. So that it does not confuse you. Yes, what you are doing is not the exact the exact register, but at least the operation would essentially be the same. And you know, I don't want you to get confused. You can start with something smaller for you to understand, and then you can shift to this one, which has a lot more variables. Okay. Very good. Now, this is not in the book, so you can do it. And if I bring this in an exam, it's also quite good to create a table, even if I've not asked for it, because with a table, then if your table is correct, then you can't go wrong. We have another another register, which is parallel in, serial out. So this is quite interesting because you input information in parallel, but then you get it out in serial. So I don't know how this thing works, because every time so for instance, this is 8. It's not that I don't know, but it's quite confusing. These are 8 inputs and your output is 1. Obviously, you can see that this is an inverse of the other, so the output is 1. Now, if you have 8 bits and you feed it into the register, yet you can only get 1 out, where do the others go? So it looks to me that you feed information in, and then if you want that word, you can take 8 times 8 clock pulses to get it out before you feed in a new word. That's quite reasonable, I think. But you also have a serial input. Okay, so this is actually a serial input. So we saw earlier that we had a serial in that had also a capability of parallel loading. This one is a parallel in that has capability of serial input. We have the clock and the clock inhibit, and we know how these work. And we have the shift and load, and we have our two inputs here. So the table is quite easy. You can see that if we are loading, then the clock, we don't care about the clock, neither do we care about the clock inhibit, which is quite interesting. And then we perform parallel loading. What does this really mean? It means that parallel loading, yeah, does anyone want to try? What does this mean in terms of operation? That we don't care what the clock is or clock inhibit is. Anyone wants to try in the chart? Let me see. Why is the clock represented by CP, not CL? Okay. Actually, the clock is represented by so many symbols, Nyeko. So you should go and read, I think, chapter 5 of the book. You'll find so many other ways you can represent the clock. It can be, so CP is clock pulse, for instance. Clock, it can be a number of things. Guys, what do you think it means when we don't care about the clock? While we are loading, we don't care what the clock is and what the clock inhibit is. We will still parallel load. It really means that parallel loading is an asynchronous operation. If it was synchronous, then we would need the clock. Yeah, thank you, Marvin. Now, if we have a high and a high, if CP is a high, clock pulse is a high, it stays high, nothing, we cannot do anything. So no change. Because you see, when it is high, we are shifting. But what does this mean? That shifting is a synchronous operation. It must wait for the clock for it to operate. Right. We are still going to shift, so the rest of these are shifting. But if this is a high, the CP inhibit, the clock inhibit is a high, we don't care what the clock is, still no change. The only times we shift is if one of these is a low and we get the right clock transition, then we can shift. Actually, this shows you that you can put your clock either on the clock inhibit or on the clock pulse input. It doesn't really matter since they are going through an OR gate, but I think it's reasonable to assume that that your clock should go to the clock pulse input, and the clock inhibit, you can keep it either a 0 or a 1, depending on the functionality that you would like to achieve. We have an example here. We see several clock pulses up here. We see shift and load. So for instance, at this point, we load. And we know that we load, in this case, this is the same 74165. Parallel loading is asynchronous, meaning that the moment we have a 0, we load immediately. We don't wait for the clock pulse. Now, this information is given to you for loading purposes. This is the information. In this time, you can load this. After this time, the loading input changes to that. Otherwise, you have your DS. Okay. So let us see. Okay. Let us see. At this point, and this is a positive going transition, so we are looking at these points. Okay, these points are the ones that we are interested in for the synchronous operations. Okay, right. Now, in this time period, we are going to shift this information. We are going to load this information into the register. How do we do it? This is a 0, which I believe is, you can see from here, this would now be 0, 1, 0, 1, 0, 0, 1, 1. So we should have a 0, a 1, a 0, a 1, a 0, a 0, a 1, and a 1. Now Q7 is being shown in red because it is what you actually get. You never really see what is happening inside since you cannot see the flip-flops and there are no points for you to tap the signal and know what it is. But really clearly here it shows that for you to be able to get Q7, you need to know what's happening inside unless you are a genius, and some of you could be. Right, now we are going to start shifting. We are going to start shifting. I think maybe this was, I think this is kept to 0. I need to look at the question again, but let's assume that it is 0 for instance. It means that this 0, when we shift after our first clock pulse, this 0 shifts here. This 1 shifts there. This 0 shifts here. This 1 shifts here. This 0 shifts here. 0 shifts there. That 1 shifts here, and that 1 goes. Oh, that 1 goes out. Of course, it is pushed out, and you continue going through this and get that performance. Now, another way you could do this, of course, is to draw a truth table. Now, it means that in the next shift, it means DS is kept at 0 for sure. The next shift will have a 0, and now that 0 will come here. That one, the one here will come here, will go down here, but the 0 from here will come here, and so on and so forth. So once again, this is something I'm going to leave for you to go and go through once again. But if you had a table, if you have a table, then you don't need to draw all of this unless it has been asked for. If you have a table, you can just go quickly to this one. By the way, if we continue here, you will notice that here we keep counting until this point, until this point. The moment the load goes low, we load immediately. We don't wait for that clock pulse. We load at this point. And what do we load? We load a 1, a 0, a 0, this new value, a 1, a 1, a 0, a 1, a 0. Now, the next time the clock transition comes on here, we are still having a load command, and so the clock doesn't matter. I think you remember here that when load is low, these ones do not really matter. And so we are going to maintain the same state, 1, 0, 0, 1, 1, 0, 1, 0. It is until the next one that the register is back into shift mode that we can begin shifting again. By the way, I have set up Muele for you. There isn't much on there, but we are required to set it up, and so I've set it up. Your self-enrollment code is 2122. And on there is the URL where you can find the videos for these recordings. There is also the book on there. I want you to read the book. Once again, I emphasize that. Now, I want to tell you that I'm not going to upload all the videos, because if I upload all the videos, you know, some of you will never attend the class. So I will choose which ones to upload. I would personally want to attend all the classes, but I will try and upload some of the videos. Now, I also know that one of the classes usually breaks off at 11. I think computer engineering. I don't know if you guys have a class, but if you have a class, you can leave. I will continue teaching for a few more minutes, not just minutes, some bit more of time until I finish this chapter. You can always see the video. But if you don't have a class, then obviously you can stay with us. Now I have this new, the last one. This is SIPO. Serial in. Is this SIPO? Yes, it is SIPO. Serial in, parallel out. And you can see that here, our input is quite strange because it is an ANDed value of two other inputs. So our input into into the register, you get two values or two variables, A and B, and add them together. Maybe for some purpose, they do this for some purpose. Okay. Now you can see we use D flip-flops, and we know with D, when we are shifting, what is at D goes to Q once we shift. And so we are shifting all through this, but we also have access to a parallel output. You know, we can at one point say we need all our information, but the information will still continue to shift through the flip-flop and come also out at Q7. I think you can see that much as we have an output at each of these, but actually we continue and connect these flip-flops in a shift, in a serial manner, right? The other thing is the clock. If this is a 1, that is a 0. And CP is a 1 here, so it needs to be 0 for you to clear. No, for you to it's a negative going transition. So if my clock is like this here, it means here it will, you know, I'll be using NGT after the inverter. Here, this needs to be a 1. If it is a 0, then it will become a 1 here and a 0 here, and then I will master reset. MR is master reset. So I should keep it a 1 so that it can shift to a 0 and a 1 here. And even if that signal goes into that, it will not make any difference. Now our two inputs are shown here with an AND gate. This AND gate is within the IC, so you don't really see it, but here they've drawn it there for you to know that yes, it is embedded within the substrate as part of the integrated circuit, but we know that we are ANDing A and B for us to get the input into the most significant bit flip-flop. Master reset, once again, needs to be 0 for you to master reset. Otherwise, it should be a 1, and we have our parallel outputs there. Now, here we see an interesting interconnection between this. First of all, A and A are kept high, meaning that if you look at this, if this is high, that will be high, meaning that as we shift, we are making everything high. Okay, we need to remember that. The other thing is that when Q7, the output at Q7, when it comes out, it goes into the master reset. All right. So they need you to know, we need the application of this by assuming that we are initially, assume initial clearance, meaning everything is at 0. If Q7 is 0, this is where we need to begin. If Q7 is 0 and this 0 is coming here, we have a 0, meaning that we have a 1 here. If a 1 is going into here, we cannot master reset. It is only if Q7 was a 1 that this becomes 0 and we master reset. So let's see. We have a 0, 0, 0, 0. And because the input is 1 and everything is 0, the input is 1. When we get the right clock transition, the 1 here will shift here. The 0 which was here will shift here. Then it will, the 0 which was here, and so on and so forth. Now, when we get the right clock transition again, we get another 1 here. And this now shifts there. Now the 0 goes there. And so this is what is happening here. We have after our first clock pulse, we get a 1 because that's the input, which pushes all these zeros there, and that 0 is lost. We get our second clock transition. I think, yeah, that 0 is lost. We get our second clock transition, another 1, that 1 is pushed there, that 0 pushed there, that 0 there, and so on. That 0 is pushed out, that one goes to Q7. And so you can see that as we keep shifting, the ones will continue shifting towards the output. At one time, everything will become 1, meaning that at some point, this value will come there. The moment it comes here, Q7 becomes a 1. It will come, it will circulate on this line and become a 1 here. And when you have a 1, we have a 0 here, and we have a 0 here, it will master reset the whole register. By master resetting, we go back to 000 and keep and do the same thing again. So this is short-lived. It doesn't wait for what it means is that the master reset is an asynchronous function. You will not wait, you do not wait for the clock transition to master reset. That's why this is short-lived. It is just a temporary state. Okay, any questions so far? Okay, if there are no questions, I'm going to take a short break of 5 minutes. Please be here at 5 past the hour, and we continue. See you in a moment. You can have some water maybe. Okay, so is it okay when you share the slides with us? No, it's not okay. These slides are my own slides, and as you can see, they are thin. There is nothing in there. They are just pictures. So I cannot share them with you because they are not good, first of all. But also I want you to read the book. I don't see why you need these slides. Besides, if you look through the videos, at least for the videos that I'll upload, now that, yeah, the videos that I will upload, you can still see the slides, you can see what I'm writing and so on. So Marvin had a question. So what would be the total delay if we have both asynchronous and synchronous? Would the synchronous override or the synchronous? And that's what would be the maximum frequency. I actually don't quite get the question, but basically these two there's no need for us to worry about the delay here. Yes, the delay is in there and we've talked about it before, especially with counters. But synchronous and asynchronous functions do not happen at the same time. And so I don't quite understand the question you're asking here, particularly when you go to frequency. We worry a bit about frequency within the counting, within counters, but with registers, you know, yeah, so you know that there will be a propagation delay across the flip-flop, but maybe you mean the clock frequency, and if there is an issue with the clock frequency, you can deal with it. Maybe we could go deeper into trying to discuss that sort of thing, but it's not something that we cover within the registers. So let us continue. The 160 and the 163, I think, are counters. And so I don't know if you are taking us back, essentially. But let us continue with the lecture today. We have two other interesting types of counters. One is the ring counter. So these counters count. We are sort of jumping back into counters. These are counters that count states. So they have unique states that we can see. Now, this is also, a ring counter is also called a saturating shift register. So you can see that usually at the output here, we would have our output going out. But in a ring counter, what happens is that you feed back this information to that input. So you can see that there is no outside input, no external input. We have the output of the counter being fed back this side. So usually you can say, let me start with my Q3, Q2, Q1, Q0 at say 1, 0, 0, 0. You usually make sure that one of the states of these is a 1, the others are 0. This is the best way to do it. You shouldn't start with all 0 because the thing will just stay as 0. Now you can see that after the clock pulse, instead of dropping this one is now going in here. So this 0 will come here, this one will shift here, this 0 will shift here, this 0 will shift here. Then we count again, meaning that that 0 shifts here, this one 0 shifts here, this one shifts here, and that one 0 shifts there. On the other count, we are going to have that 0 going all the way back here, this 0 coming here, that 0 coming here, and that one coming there. And now, if we count, if we give another clock, we are going to have 0, 0, 0. So you can see that actually, after this state, we recycle. That means that we can have 1, 0, 0, 0, 0, 1, 0. I should go here. 0, 1, 0, 0. 0, 0, 0, 1. No, it is 0010. Okay. And then finally, we have 0001. This is our state transition diagram. So this means that we have 4 states, because you can see it just recycles. So if you keep applying clock transitions, we are just going to keep circling in this direction. And so this means that this ring counter is a mode 4 counter. It doesn't count the way the binary counter counts, because the binary counter would start oh, yeah, I've been muted. I don't know what happened. Interesting. Is the network poor? Yeah, sorry, I don't know how I muted myself, but it's okay. I'll just repeat this. I'll just repeat this for you. Right. Once again, we can see that we have, okay, let me just go back here. Yes, once again, we can see that, okay, if you started with Q3, Q2, Q1, Q0 at okay, all right. I think I'm back. Hopefully now you can hear me. So as I said, we get one of the inputs, sorry, of the flip-flops, we make it 1, and then the others will be 0. As you can see, Q0 is fed back to Q3. So that means that this is the initial conditions. We can say clock are 0. After the first clock, that 0 is fed back to Q3. It will come to Q3, so 0 here. This one shifts here, that 0 shifts here, and that 0 shifts there. On the next clock, this 0 is fed back to this side, meaning that I don't know why I'm having a bit of a problem with this. All right. Yeah, so that is fed back there. So meaning that that 0 comes here, this 0 comes there, that 1 comes there. Oh, that's a 1, and that 0 goes there. And on the third count, we have that 0 going all the way back here, that 0 going here, that 0 going there, and that 1 going there. Now, this is basically where we stop with the counting, because we see that on the fourth pulse, this one will come back here. Then you have your 3 zeros, but this is equivalent where we started. So that means that after this state, basically we cycle back to that one. These are 4 states. You have 1, 0, 0, 0. You have 0, 1, 0, 0. You have 0, 0, 0, 1. And you have 0, 0, 0, 1. This is 1, 0, 0, 0, 1, 0. So you have these 4 states. And if you had started here, this is your transition. Now, I had explained this, but I think I was muted, that actually what happens is that much as this is not a binary counting, we are not moving from 0 to say whatever, but it is still counting because these 4 states are unique. And so we see that we have, since these are 4 unique states, we can say that this is a mode 4 counter. Now, if we had these 4 flip-flops with a binary counter, we would have mode 16, if you remember, because this is from 0000 to 1111, 16 unique states, which means that this is a huge disadvantage for this type of counter, the ring counter, because the number of the mode number is equivalent to the number of flip-flops. In other words, you need so many flip-flops to create this. The reason why this might find application in some scenarios is because the reason why you would do this is because obviously that this counter does not need decoding. We talked about counter decoding. We don't need decoding here because, as you can see, in each scenario, just one flip-flop is high or the others are low, and so it's very easy to know or to decode the output. How come you cannot hear? I thought now you should be able to hear. Yeah, I believe that you'll be able to hear me. Great. Thank you. So, if we come back to the next slide, you can see this is precisely what we have done. This is the truth table. At most, just one flip-flop is high, and so it's easy to know which one is high. That's why we do not need to decode. The other thing here is that you can see that if you look at these, obviously these are going to repeat. If you look at, for example, Q3, at this, if we look at that point to that point, it will repeat again after that point. So the frequency of this one, for the clock, if we take these 4 transitions, okay, this one has repeated 4 times, and this one in the same period has repeated 1 time. So it's safe to say that the frequency of, for instance, Q3 is the same as a quarter the frequency of the clock. And all of these have the same frequency actually. This is same frequency. All of them are quarter of the frequency of the clock. So if we need to create a mode n ring counter, we need n flip-flops, which I've said is a huge disadvantage when you come to, if you compare, for instance, with if you compare it, for example, with a binary counter, which would go through the normal states. What else do I need to speak about this? Yeah. Okay, so how do we ensure that Q3, Q2, Q1, Q naught is, for instance, 1000 initially? Because you see, we said that for this to work, you make sure that at least you make sure that one of the inputs is a 1, the rest are 0. How do we ensure that? I think we talked about it before, that we can first clear, you can say first clear everything, meaning that you are in 00000, and then preset flip-flop of choice. In this case, Q3, so you have 1000. Then you can start to count, because we say that usually when you switch these things on, depending on the spurious signals within the wires, sometimes you may not be able to predict the initial state in which these counters are, and so we might need to preload. Marvin, you are trying to convince me to upload all recordings. And the best thing I can say to that is that no, I will not upload all the recordings. Because you see, right here, I see about 80 people, which is great. I didn't expect that 8 of you will attend. But where are the other maybe 80 people? You see, that's a that's a big question. Anyway, I will upload most of the videos. I will not upload all of the videos. I don't think 5 videos, are going to make anyone fail. We have another. I've already said I'm not going to give the slides. These are just my slides. These things are in the book. I didn't pick anything from outside. The Johnson counter is a modified ring counter. For it, the ring counter, the feedback was coming from this input, the normal input, output. For the Johnson counter, we feedback the inverted input. That's what we do. We feedback the inverted input. So it's quite similar, but we will see that actually it has certain interesting advantages. Let us look at an example of Q3, Q2, no, Q2, Q1, that's the example in the book, and Q naught. Now here, we have clock. With the Johnson counter, the other thing is that we can start from a clear position. We can start with all flip-flops cleared. Before, with the ring counter, we needed one of them to be high. Here we can start from 0, 0, 0. This is before the clock pulse. After the first clock pulse, the inverted input of this is fed back. It is the inverted input. So we would have a 0 here, meaning we have a 1. So it's a 1 that is fed back here. And so that means that we are going to have a 1 that shifts to a 0, that shifts to that position. On our second clock pulse, this shifts here, this 1. That shifts here, which is a 0. This 0 now we take back its inverse, which is 1. And 3, we are going to have this 0 coming here as a 1 because it is the inverse. That 1 is there, and this 1 is there. Okay? Now, we are going to see 4. 4, this goes back as a 0. Now, this one shifts here, this one shifts here. 5, this goes back as a 0. This 0 comes here, it's a 0, and this one comes there. And then we say 6. Now, this one will go back as a 0, and that 0, and that 0. Meaning that from this state, we cycle back to that state. How many unique states are these? 1, 2, 3, 4, 5, 6. So for 3 flip-flops, we have a mod 6 Johnson counter. Now, if it was a ring counter, we would have mod 3. So you can see that a Johnson counter increases the mod number that you can derive out of the flip-flops that you have, but it is still not similar to, so it's double the number of flip-flops. For the ring counter, the number of flip-flops is equivalent to the mod number. For the Johnson counter, the mod number is twice the number of flip-flops. Obviously, for the ring counter, for the binary counter, the mod number is equal to 2 to the power n. In this case, because these are 3 flip-flops, we would have 8. Okay, so you can see that the Johnson counter sort of gives you some middle ground between these two. Unfortunately, for the Johnson counter, now from here you can obviously draw the state diagram from 0, 0, 0, 0. Here you have 0, 0, 1, and here you have 1, 0, 0, going all the way through that. Okay, let's see. I don't know how to help people who can't enroll themselves. I don't know. I thought if I give you the code, it should be able to enroll you. So we can't have more than one flip-flop being high at the same time, say 1100 for a ring counter. No, I would really like you to, Isaac, I would really like you to go and try it and see what it would look like. But I think the right and normal operation is for us to have one flip-flop. We are going to do something called decoding, flip-flop decoding. With the Johnson counter, you have got to decode. And the decoding requires you to identify unique states. This is actually, we are now going to do decoding. And if you have 2 ones, you might have a very big problem. So with the Johnson counter, we need to decode. What do I mean by decoding? It means I need to identify the state in which I am, the count. If I'm counting to 8, I need to know, am I at 6, 7, 5? That is decoding, and we saw this in the last lecture. So let us look at this case. How do we decode? Before we would have, let's say CBA, we had 000, 001, 010, 011, and so on. We were saying that for us to decode, we say we get an AND gate. In this case, everything is inverted, okay? Right, like that. And we say CBA inversed, because we know these will be zeros, so that we have a high. And this is the only unique combination out of all of these, because the rest are 100, 101, 110, 111. In other words, if we have similar AND gates, this is CBA, all of them will be low except that one, because if I'm at 000, this will give me, this AND gate will give me a 0. But if I'm at 00 here, this AND gate will give me a 1. All other AND gates, so for instance, this one would look like this. You have C, but B needs to go through that, and A also needs to go through that. Okay, so if I have a 000, all of these will be 0 except 1. That is what we mean by decoding. In other words, for each state, there is a gate that will give you a high, or other states will give you a low. Okay. So now how do we decode a Johnson counter? A Johnson counter is quite different, because for it has 3 states, but we can use gates with 2 states. And at all times, whether we have a 5 flip-flops, whether 20 flip-flops, we still use gates with only 2 flip-flops. That is an upside for the Johnson counter over the binary counter. Because for instance, for the binary counter, if we had 5 flip-flops, meaning we have, you know, E, D, C, B, A, it means we would need 5 input AND gates. Okay, if we have 10 flip-flops, 10 input AND gates. And so the decoding with the binary counter, much as it has a higher mod number, its decoding is a lot more complicated than for a Johnson counter. But let's try to understand how we decode the Johnson counter. Now, in each state, this is a state, that's a state, that's a state. In each state, we look for a combination of 2 values that do not appear anywhere else. Now we know that from here we cycle back to that. If I look at this input here, I can see that I have a combination of Q2 as a 0 and Q0 as a 0 that does not appear anywhere else. There is no anywhere where Q2, Q0 is 0, 0 except in the first state, which is why I can use that to decode the first state, okay? Which is, as you can see, I can pass that through this AND gate. And if I look at the next state, do I have a 1 and a 0? No, I don't have a 1 and a 0. So once again, I can use this one as Q2, which is a 1, and Q0, which is a 0. You can see that is the case. For this one, I can have, do I have a 1 and a 0 anywhere else? No, I don't have a 1 and a 0. So I can use Q1, which is a high, and Q0, which is a 0. And I think you can see that to be the case. Now, I can come here and look at this one. I have 1 and 1. 1 and 1 also appears there, so I can't use it. Yet 1 and 1 also appears there. I cannot use it. But there is no 1 and 1. So here I could use Q2 and Q0. Because there is no anywhere I have a 1 in Q2 and 1 in Q0. I think once again you can see that. Here I have 0, 1. There is no anywhere I have a 0, 1 in positions Q2 and Q1. So Q2 bar Q1. And then 5, I think it is that one, which is Q1 bar Q0. I'm sure you might have some questions on this. Now you should remember that Q2, Q0 appears twice with 10. You cannot use Q2 and Q1 bar. I don't know, you should show me where exactly with 10, with 1, 0. With 1, 0, where did I use 1, 0? There is 1, 0 here. Where else is a 1, 0? Here. No, I mean 1, 0 in these positions of Q2 and Q1. This 1, 0 is in the positions of Q1 and Q0. Okay, so yes, in this state I have 1, 0, 0. In the next state I have 1, 1, 0. So here I can use this combination, which is Q2, Q1 inverse, and here you use Q1, Q0 inverse. That is okay. It is not a repetition. Can you use other gates to decode it? Yes, you can use NAND gates, Vanessa. We looked at last time, we saw active high decoding, which is the case here where your output goes high and then the others are low. But you can also use active low decoding where you have some of the inputs Yeah, sorry, where the decoded output is low and all of the other outputs are high. So you can use NAND gates for something similar. Now, let me see. So let's see. Now we have a scenario like this. This is also a Johnson counter. Richard asks a question. What do we base on when choosing combinations, say Q2 and Q0 or Q2 and Q1? We look at any two combinations which we look at a combination of two inputs or outputs in fact that does not repeat itself. It does not repeat. So that's why if I look at, for instance, let's say we have, actually, I want to, let me copy this just briefly. And then I'll put it here. This could be a bit complicated. I totally appreciate that. But actually you will notice that once you learn it, it's very easy. So we see here, we are looking at combinations of this. So either Q2, Q1, Q2, Q0, or Q1, Q0. Now, if I look here, I see that Q2 is a 0, Q1 is a 0. Q2, Q1 also repeats here in 5. So if I can't take 0, 0 because it also repeats here. Now I look at the next combination. What about 0 and that 0, which is now between Q2 and Q1? What about that? I realize that actually that does not repeat anywhere. So that means I know that now it is Q2 bar, Q0 bar. I go to the next combination. I can have a 1, 0. Does it repeat anywhere between Q2 and Q1? No. So that is my combination. Q2 is a 1, Q1 is a 0, so a bar. I come here, I see 1, 1. 1, 1 clearly repeats here between these two. Whereas Q1, I have a 1 and a 0. Does it repeat anywhere? No. So I can have Q1, Q0, bar. I come here, I have here the only combinations possible are 1, 1 for sure. But this 1, 1 is also here between Q2 and Q1. What about the 1, 1 between Q1 and Q0? It also happens here. What about the 1 at Q2 and 1 at Q0? It does not happen anywhere else. So I know that that's Q2, Q0, and so on and so forth. That is how you identify. Oh dear, what happened? Today I'm having a lot of issues with my Zoom. Is the screen showing launch meeting? Can you see the slides? Yes, a lot of you seem, some of you are the ones confusing me actually. Let us look at this one. This one is just a mode 4 counter, Johnson counter, mode 4. This is a simple one, just 2 gates, 2 flip-flops, 0, 0. So the next time we feed back, this 0 is fed back as an inverse, so 1, 0, that one comes here. That one will be fed back as a 1, that one comes here, and 0, 1. So we have 0, 0, 1, 0, 1, 1, and 0, 1. In this case, there is no need to decode because as in it, there is no need to look for combinations because clearly you can see that all of them are different. It's 0, 0, so we can have a gate there, 1, 0, a gate there, 0, 1, 1, a gate there, and 0, 1, a gate there. What about this one? Let me make a copy actually so that we have a bit more space to discuss. And I will delete this. Right, now, I created a mode 8 Johnson counter. So you can go and do this one in your free time. You just need 4 flip-flops, not 3. 4 flip-flops. The one in the book, the example is 3, just do 4 flip-flops. You'll notice that this 0 is fed back as a 1, that 0 will be fed back as a 1, that 0 will be fed back as a 1, that 0 will be fed back as a 1, 1 will be fed back as 0. But at some point you stop here because then you go back to 0, 0. So that means this state goes back to that. That's because we have 4 flip-flops, and we said if we have 4 flip-flops, the mode number is double that. Now, we want to do some decoding. Unfortunately, I've already done the decoding for you here. But if you look through here, we can start to look for states that are not there. If, for example, you look at this 0 and this 0, you look through again here, you can see that it is appearing both there. So that's not going to work. What about Q3 and Q1, 0, 0? Does it appear anywhere? Yes, it appears in this case. So again, it's not going to work. What about Q3 and Q0, both of them 0, 0? Does it appear anywhere else? No, it doesn't appear anywhere else. So that means I use those inputs to decode, which means I have Q2 because it's a 0 and Q0, which is a 0. Then I go to this one. What about 1, 0 for the next state? 1 and a 0. Do we have a 1 and a 0 here? No, we don't. So that one can actually, I have got Q2 and Q0. Let me see. What about a 0 and a 0? Oh, so this one is actually wrong because a 0 and a 0 also appears there. So actually the answer is I have Q3 and Q2. Yeah, because I don't have, no, Q3 is not a bar, okay? Q3, Q2 bar. Now, what about this one here? 1, 1 clearly is there. 1, 0, is there 1, 0? There is no 1, 0. So I can have Q2, Q1 with a bar. What about here? I have 1, 1, 1, 1 is there. 1, 0 is 1, 0 there? 1, 0 is not there. Is 1, 0 there? Oh, 1, 0 is here. This one is 1, 0. So I'm looking at, what about 1, 0, this one? Does it appear anywhere else in here? No. So I can have Q1, Q0 with a bar. And so you continue like that. You will maybe I've made a mistake in here, but I can see, for instance, that here we have that and that, which is Q3, Q0, and so on and so forth. And you can figure out how to do the decoding for these types of counters. It is Q3 bar, written bar, Q3, supposed to be Q3 bar and Q0 bar for clock 0. Okay, I mean, I couldn't do the equation, so that's what I mean, you know. B, Q3, I mean, is equivalent to Q3 bar. Okay. Yes, that brings us to the end of this lecture and also to the end of that chapter on counters and registers. We are going to start looking at some other digital devices like flip-flops and coders and decoders in the next week. I intend to give you some homework. And so when I give homework, it will be group homework. And so you should already be figuring out who you are going to work with. You've done this with me before, so this is not strange. You create groups of 5 to 6 members, and I want to see a mix of computer engineering, electrical engineering, telecom engineering, and so you all get same marks. Okay, I don't want now, again, guys, we are not face to face, you know, there's corona, so I don't want to see people coming to say they want to do alone, or you know, they didn't get the memo, you know, stuff like this. We shouldn't have that thing. I'm giving you time to create these groups through your representatives, and so please take the time to create these groups. Maybe in the next week I'll throw down an assignment, and I don't want to see people panicking. Otherwise, have a nice day, and see you soon.